Welcome to chapter 29. We are trekking our way through the stellar and galactic class. We're going further and further into the ends of the universe. So what we're going to do today is we're going to really go back to the beginning and see how things were at that time and see the different kinds of theories. One of the things you may notice, unlike most of our presentations here, most of our slideshows, this one has a lot of text on a lot of the slides. So I'm not just going to read it to you. I'm not a read PowerPoint and be that kind of guy. So there will be times that I'm going to recommend that you sort of pause the video and read the stuff for yourself, and I'll highlight some of the key points in some of them. Some of this gets pretty esoteric. Some of it gets pretty sort of heady kind of stuff. And that's okay if it's a little bit confusing along the way. We're going to talk about different things that are actually changing even as I'm probably speaking, because this is one of the cutting edges of astronomy right here as we're talking about this stuff. So please bear with me and let me figure out, again, sharing screens so that everyone can see everything I'm doing. We don't need that, and I certainly don't need that. So we will be in the beginning, the Big Bang. And our slideshow starts now. Okay. What you see behind me in my sort of virtual background is a portion of this. This is the James Webb Space Telescope. This will be the successor, not really the replacement, but the successor of the Hubble Space Telescope. One of the things you may notice as I'm watching this slide with you, currently planned for launch in 2018. Well, guess what? It's still on the ground. So yeah, this is a very, very long-term project. And because we don't have a space shuttle to get up and repair it if there's an issue, like what happened with the Hubble when it was launched, we need to make sure it's right the first time. It's also going to be much further out than the Hubble, and the mirror is quite a bit larger than the one for the Hubble. So as you see, it's 6.5 meters. It's 21 feet in diameter. That is quite significantly larger. The Hubble mirror would have fit very closely, very sort of easily within this area in the middle here. So the Hubble would have been right in there, and that circle may be a little bit too big actually for it all. It's going to make a difference when we actually get it up there, and hopefully, like the Hubble, it will last for decades. But when we're talking about this issue, we're really talking about stuff that originated with Einstein and Hubble. We've talked about both of these guys before, so I won't bore you with too much biography, except to tell you that when we're talking about astronomy, frequently we are talking about two different areas of discovery and research. We're talking about people who do theoretical ideas, and we're talking about people who do practical things. You can be the astronomer who was at a blackboard doing equations and never looks up at the sky. You can be the guy at the telescope who never really even deals that much with mathematics. So both ways are ways that have been known as valid ways of doing astronomy, all the way back to my guy Tycho with the fake nose. He would have been the forerunner of Hubble here, looking up at the sky all the time, and Kepler, who would have been the guy who is the forerunner of Einstein, coming up with all sorts of equations. Now, it's never so cut and dried as that. The people who do research often do look at images, look at various pieces for confirmation, and people who do the observations do need to do some mathematics along the way to keep themselves grounded in what they're doing. But there is a division of labors, a separation of labors. When we're looking at things that are far away, we're looking at things that were far a long time ago. Far from us in space is also far from us in time. And as we look at these different areas, we look at supernova in particular, because that's one of those standard candles. If you remember a few lectures ago when we were talking about how we measure things, how far away things are. And the farther away things are, the dimmer the supernovas will be, but we know how supernovas work. So we know that, okay, that's a 100-watt bulb here, it's a 100-watt bulb here, it's a 100-watt bulb here. So we can measure what the light is likely to be, and therefore we can measure what the distance is likely to be. Also how far back things are, and we've been able to trace things back very, very, very far. Now, one of the things that we've discovered as we're looking at these things is that the universe is expanding. Hubble figured this out from different what we call the redshift. Cosmological redshift is the term we tend to use when we're talking about the expansion of the universe. That has been aided in more recent times, not just by looking at galaxies, but by looking at supernova and other Cepheid variables and other kinds of things like that. One of the things we've discovered is that not only is the universe expanding, but it's accelerating. What is causing that acceleration? Well, we don't really know, but something is, and that's dark energy. That's sort of the sort of corollary to dark matter. Dark matter is affecting us gravitationally, but we can't see it. Dark energy is affecting us expansionally. And is that a word? I don't know. But we can't see it either. As we look at what has happened in the past, we can sort of notice that things sort of trucked along in different ways, and we, not rather than just going steadily up, we sort of have these bump outs at different points, and we don't know exactly why those bump outs occur. So we call that dark energy, and that's one of the ways in which we are looking at how the universe expands. Just to show you how things change over time, no pun intended there. When I was taking this class 35 years ago, the figure that's on this slide down here, 13.8 billion years ago, that would have been considered to be way, way too young, and we would have been talking about a 20 billion year old universe. But once we figured out that there were areas where it was expanding faster, it wasn't just expanding uniformly, that means the time goes down because the rate of expansion goes up. So we have a couple of different things that are happening here that keep revising this number. So this is one of the areas of astronomy to watch out for revisions. Just like whenever you look at Jupiter and they ask how many moons does it have, you really need to check NASA to see how many moons today, because they may have discovered more. When they talk about the age of the universe, this is one of those numbers that is highly susceptible to change. In the beginning, things were much closer together. Gravity was much, much more of a powerful influence. As things separate out, of course, the influence of gravity weakens, because the further away things are, the less gravity there is. So as we watch what's happening in our universe, we're seeing things expand away. Well, to figure out what happened before, we run the tape backwards. Do we still have tape? I don't know. I'm showing my age. We run the video backwards, and we see that things get closer and closer and closer together until they hit the jumble. The term Big Bang was sort of a term that was thrown out there almost as an insult. It's like, well, did everything just sort of start with a big bang? It's like, well, they sort of kept that. So be careful when you name things ironically or in sarcasm, because sometimes those things stick along the way. So we have people like George Gamow and Ralph Alpher who figured out that the earlier days would have been much hotter, much denser, and as things began to expand out, then we have a cooling effect. But as things are in that kind of density and that heat in the middle of the beginning, we're going to have a much fuzzier, literally fuzzier idea about what's happening, all of this. The key question that people keep asking is, where did all of this come from in the first place? What caused the Big Bang? That's another cutting edge area of astronomy. And of course, some people have difficulties figuring this out and accepting it. It was Freddie Hoyle, Fred Hoyle. I'll say Freddie because I met him and I know people who know him well enough that he's Freddie. He did not accept the idea that the universe was, or started with a Big Bang. He said that the universe was always there, and if it seems to be expanding, it's expanding in areas, in pockets locally, but there are areas out there that aren't expanding and we're expanding into them. And there's somehow new matter being made in different parts of this to keep everything going. And they call that the steady state model. That's pretty much been discarded by, I would say, 98% of astronomers, maybe 99.999 of them. There are still a couple of holdouts for the steady state theory. Because one of the things that Hoyle would say is we have to have some mechanism for new matter to be added. In our quantum ideas, we might be able to have some new matter added, but there are too many pieces of evidence that show the expansion going on and the earlier contraction that wasn't the same as before. And that's what really kills this steady state model. When we're looking at things further back, things aren't the same, just older. They actually do change as what we're seeing. And if it were a steady state, we would not be seeing that kind of change along the way. So Hoyle's idea is as sort of an interesting sideline to that, the steady state theory. It's worth knowing that that's out there, but it's pretty much one of the theories that isn't accepted anymore. One of the things that we can do when we're looking for older things and trying to figure out how things used to be is we look at globular clusters. We've covered these before when we were looking at stars. Remember, our galaxy is a disk around a bulge that has most things going around in that disk and bulge, but are also around, we have these collections of stars going every which way. Globular clusters can have 100,000 to 1 million stars held together in their own gravity. They are older than our galaxy. And thus, when we're looking at that, we're looking at things before our galaxy. We're looking at things that were older than us, and this is how things used to look earlier than we did. We are, again, in addition to the James Webb Telescope behind me here, building more and more larger telescopes. As I mentioned a couple of times in class before, the Atacama Desert in Chile offers a wonderful spot for low cloud, low atmospheric interference, low city light interference. And we have a couple of different things that are being built out there right now, including things like the Very Large Telescope, which is here in the middle, and the Extremely Large Telescope, of course, not too creative in their naming here. But this is sort of by size comparison with the Colosseum in Rome. If you've ever seen Gladiator, then ta-da, there you go. And so these are pretty big facilities, but you have to have things this large to match the power of something that's behind me. And that's a big telescope that's behind me here. But this telescope here would fit in my house. These things would not. So yeah, I mean, I don't have a house that's big enough that this would be in the living room, but I mean, it would like the whole house. When we're looking for things that are far away, and by far away, I mean 13 billion light years or more away, the very edges of our observable universe. We need those kinds of things because one of the things that happens is as space itself expands, the light rays get expanded and we have a redshift. These expansions then push it into lower and lower energy areas. Remember, blue is high energy, red is low energy. So this stuff is incredibly low energy along the way. So when we're thinking about the beginning of the universe, we're also thinking about the ending. So as we think about the Big Bang, we think about, okay, how does that happen? How does that sort of play itself out? And we have a couple of different ways of thinking about things depending upon, in large part, how much stuff is in the universe. And when I say stuff, I mean matter, which includes dark matter, energy, which includes dark energy. You have to include all of those things. And we have an idea where we have decelerating universes, where we're sort of expanding like there was a sort of an explosion, although the Big Bang technically wasn't an explosion, but we can think about it in terms of an explosion that will sort of run out of energy. And then, of course, as it sort of runs out of energy, the gravity takes hold and pulls things back together. We might think about the Big Bang ending in a big crunch. What happens then? Well, there's one theory that we're sort of oscillating Big Bang to Big Crunch. And that's a new Big Bang to a Big Crunch. And we have these sort of over and over and over again universes. Or we have a decelerating universe where there's enough matter to slow things down, but not enough to pull everything back together again. So we sort of end up in a longer term steady state, but we wouldn't have always been in a steady state. So we're kind of sort of looking towards Hoyle in a certain chunk of our universe's history, but not the entirety of it. Then we have the coasting universe, where there's not quite enough material to slow things down, but we don't keep going faster. And then we have the final one, the accelerating universe, where there's some extra energy that seems to be pushing us to faster and faster accelerations. This, combined with this, seems to be the model that we're following right now in terms of what we're seeing. And we can see this sort of plot here. These correspond to what was there before. Curve 1 here, if we have critical density, means you have enough stuff inside to pull everything back together. Critical density pulls us back into a big crunch. Curve 2 and 3, these are sort of right at the edge of where we would have enough to slow us down or just keep us going at a steady rate. And 4 is where we have not enough to keep us crunching, or an additional type of energy, dark energy, that pushes us out. So these correspond to these. You can look at those back and forth at your leisure. When we look at the deepest of deep field images from the Hubble, we can sort of see this here. We can see these little numbers here. These are inserted. They're not just out there in space. These are called our Z redshifts. And the higher the number, the faster it is pulling away from us. We have one that may be measured at 11.9. This would be very, very shortly after the Big Bang itself, less than 1/3 of 1 million, or 1 billion years after that. So we're talking more than 13 billion light years away. So when we're looking at these things, we are looking very, very far back. We're looking into the sort of toddler years. This may be even sort of in the just post-infancy years of the universe. These would be sort of toddler years and very early childhood years of our universe as we're looking at these. So Lemaitre here is, as you can see, he's wearing the collar. So some of us are priests as well as physicists. This guy studied Big Bang and relativity and other kinds of things right when they were new. This is one of the few guys in the world who could write a letter to Einstein and say, you know what, you're probably wrong on that. And Einstein would listen to him. But he actually was someone who looked at Einstein's ideas and predicted that this expansion was going to be a feature of the universe, if that was true, before Hubble actually measured it. And so we might actually sort of think about what's going on there in terms of who gets the credit when something is predicted versus when something is more or less verified. We have an interesting collaboration between different figures in history, including Gamow, who we've talked about before, and Alpher, who tried to figure out whether or not there was a certain substance or a certain something in the universe that was either holding things together or pushing things away. And how do we describe what things were before they are what they are? How do we describe things before they sort of solidify into protons, electrons, and neutrons, and all of those kinds of things? And what exactly is space-time? Where is all of this stuff? Is this stuff actually something, or is it nothingness in which things are? And that's been a debate for hundreds of years in astronomy and astrophysics as well. Space-time itself is described geometrically. When we're living in our everyday world, we tend to think of things as flat. In fact, we have a lot of people who still think the world is flat. And when we're dealing with that, we have to deal with the idea that locally things might look flat, but the further out we get, we begin to see that they're curved. If you're sort of an ant on a balloon, everywhere that you're looking around you looks flat, but you keep walking or walking, and you figure out that, okay, I've curved around. So when we're sort of looking at this geometry of space, space itself expanded, which means space itself contracted a long time ago. And back then, that's when things were beginning to form. Of course, things begin from a very, very hot and dense area, and they have to then separate out. How did that separation occur? That, again, is one of the hard areas of astrophysics. We use particle accelerators and other kinds of devices here on Earth to try to recreate some of those early conditions. We have different kinds of leptons. And the most common one that we interact with, of course, is the electron, which gives us electronics. And then we have quarks, not to be confused with the guy from Star Trek Deep Space Nine. These things combine into making protons and neutrons. So these are inside the protons and neutrons. So we might think about this stuff as primarily matter, the stuff that we can sort of see and feel and touch, and these kinds of things as being more energetic. But these are all things that we can measure. So these are all things that we can identify, we can recognize, we can locate, we can count, we can figure out how they're being generated. When we're looking at these things, we're talking about forces and bosons. So bosons are the portions of stuff that are part of these fundamental forces of force boson. Fundamental force, which is gravity and strong forces, weak forces, and electromagnetic forces. So a photon is what is electromagnetic. So if something is magnetic or electric or light, which is coming, that's going to be one of the bosons for that. Gravity, of course, we understand strong and weak forces are the things that are inside of the atoms themselves. So we have force bosons, which are the four of them. The gravitons are still elusive to us along the way. So we have our matter here, and we have our energy here. If this is really confusing, read the chapter and realize that this is, again, tricky stuff as we're talking about it here. The main point of all of that is that those are the things that come together to form what we have in the universe. Wherever we look in the universe and see a galaxy, wherever we look and see a star, wherever we look and see a planet, wherever we look and see a comet or an asteroid or even just a ray of light, we are seeing those things. Those are the things that we're measuring. Those are the things that we are seeing. And as we look out into the universe, way, way, way back, see, we're here at the center, and we're sort of looking at the future, we're looking at the past, in terms of physics, in terms of mathematics, we can look at the future. In terms of our observation, we can look at the past. And we're seeing the same stuff. We're seeing protons, we're seeing neutrons, we're seeing electrons, we're seeing these kinds of things. The cosmological principle is that when we're looking at the universe, on average, things will look pretty similar. They'll look the same kind of stuff along the way. And as we go further and further back, that same thing holds, that same principle holds. Today, here we are, Before us, obviously, planets and stars formed. Before each individual star is younger than galaxies, but before that, we had to have atoms form, and before atoms formed, which have protons and neutrons in the middle and electrons going around, we had to have those things form. And we had those form out of the radiation. Before we get to that area, though, we're going into the earliest and earliest of parts of the universe. Notice the timing here, though. We're talking about seconds. When we talk about 10 to the 17th seconds, think about how many seconds are in a day. We have 60 seconds in a minute. We have 60 minutes in an hour, so that would be 60 times 60, which is 3,600 seconds in an hour. So we have 24 hours a day, and there we've left the ability for me to calculate in my head 24 times 3,600, then multiply that by 365 days a year, but we're still nowhere close to 17. By the time we've done that, we're still like at 8 or 9 in terms of our exponents there. So when we're talking about this, we're talking about 13.5 billion years. But notice when we're getting back to the Big Bang, we're dealing with negative exponents here. This is a fraction of a second. This is like 1/1000th of a second, and back and back and back. These things happen so rapidly that there wouldn't even be time for one electron to go around one proton before a major shift had occurred, because everything is expanding and everything is cooling as everything's expanding from the center. All of the forces that we have in the universe today, as we sort of look back further and further and further, we can see that electromagnetic forces are combined. We can treat them as separately in different ways, but we see, in fact, they are combined. Go back further and we have our strong and our weak forces combined. Go back further and we have gravity combined. That's one of the areas of research today. How did gravity combine with all the rest? We haven't quite gotten there yet in terms of what happens. But these particles, as the universe sort of spreads out and cools off, are able to combine into our different kinds of structures that we have. We have our electrons and positrons that are forming and deforming. We have our, and that's still before 1 minute. After a couple of minutes, we have the centers of atoms beginning to form. It takes a couple 100,000 years before the electrons and the atoms, the protons, the nuclei begin to form together. One of the reasons we can tell that is because as we look back into space, there comes a time, here we are at the present and we're going back in time here, there comes a time where we're not seeing anything anymore. There's nothing to see, there's been nothing formed, but there is all this radiation, there's all of this stuff that was there, and that actually permeates the entire universe, and that's called the cosmic background radiation. That is sort of what was discovered when they were looking for what was creating background static when we were trying to set up radio systems and telephone systems around the world. We kept picking up things that we didn't know where it's coming from. Well, it turns out it was coming from the universe. And the guys who figured this out were Wilson and Penzias. And they were literally just working for the telephone company and the radio companies, trying to figure out where this sort of hissing background noise was coming from. One of their thoughts was pigeons were roosting inside the antenna, and pigeon droppings have different kinds of chemical content that can react with the antenna and make them sort of less sensitive and create a static. But once they cleaned out the pigeons, there was still static there, and that was determined to be coming from everywhere in the universe. You look there, you look there, you look there, you look there. It's coming from everywhere. Now, helpfully, they were just down the road from Princeton University, where, again, the theoreticians were also working on this. So again, you have the practical guys and you have the theoreticians. When we look at this, the further and further into the universe we go, the more and more and more spread out that radiation is, the further and further back in time it was in its intensity, which means the temperature is lowering and lowering and lowering and lowering. And we are actually all the way down to 2.73 K. Remember, K is our absolute zero scale. So zero is absolute zero. So this is only a couple of temperatures above absolute zero. So we're talking like minus 450 degrees Celsius. This is a cold day in North Dakota. But we have instruments that are sensitive enough to pick this up. And as we look throughout the universe, again, we have that cosmological principle. We can see it's pretty standard. We have had different satellite observatories that have gone up, that have looked and looked and looked at this, and of course we get better and better as we do it along the way. The first one was in 1989, as you see here, our COBE, the Cosmic Background Explorer. About a decade later, the WMAP went up and got a more detailed mapping. Then the Planck went up, and it got yet even more precise, and we can see overall, on average, it's pretty uniform, except we do see areas where it's cooler and do see areas where it's hotter. We would expect that. We can see that subtly here. We can see that more and more. But it's sort of like if you look at maps of elections, and you see, well, here's a red state, here's a blue state. But then when you look at it county-wise, you see the red state has blue counties and the blue state has red counties. And then if you break that up even more, you can see even sometimes block by block. And the whole country then turns really purple by the time you're looking at that, rather than blocks of red and blue. That's what's happening as we get more and more sensitive equipment. And when we get up above the atmosphere, we don't have the atmospheric interference. Which is why these become very important to us. Well, one of the reasons why this is useful is because we're trying to find out, again, is our universe headed for a big crunch? And if that's the case, then our universe could be likened to a sphere where we sort of start at one pole and go back to the other. Are we sort of just balanced, just so that we'll just sort of continue out in a steady kind of thing? Again, thank you, Fred Hoyle, for that idea. It's a different idea, but it's a good term. Or are we accelerating? Are we going in, and we call this a saddle side universe? Are we expanding into different directions? So picturing the curvature is in part why we're looking for that background information. And when we're looking at these different portions of the universe, we can see that we have portions, if they were taken in isolation, would correspond to each of these three types of shapes to our universe. But when it's taken as a whole, right now, most people are thinking that the overall structure and the overall content corresponds mostly to right somewhere in the middle. So that's what we're looking at right now. But looking at it becomes a problem, because when we look at the universe, what we are seeing is really only about 5% of what is there. The vast majority, as much as 68% of what is there in terms of energy, is that pushing us apart is stuff that we can't directly detect. And about 5 times or more of what's stuffy stuff out there that we can't detect, dark matter, is also out there and we can't see directly. Dark matter is influencing us because we can tell how things are shifting and moving, so we know it's there. Dark energy is pushing the universe out even more, and so we know it's there. So that's a whopping 95% of our universe that we don't really know what it is. That's a huge amount. Now, in history of astronomy and in history of science in general, that's not unusual. So you might think, well, how is that possible? Think about the world before anyone knew there was oxygen. We were breathing it in and breathing it out all the time for thousands of years of human history without knowing that it actually existed. But it didn't stop us from breathing it in and out. We didn't suddenly sort of figure that out. For thousands of years, we didn't know really what gravity was. For thousands of years, we didn't really know what any chemicals were. We thought there were 4 elements that combined together in different ways, and we just kept trying to figure out how. Well, we now know that's not the way things operate, but those were good models. We have models that probably 100 years ago, 100 years from now, 1,000 years from now, people will look back and say, oh, why didn't they just see? That's sort of the way science operates. So we're in one of those like, oh, it's hard to figure out phases when we're looking at those. When we're looking at the universe, dark energy tells us that things are, of course, going in a faster way because we look at our standard candles and we can see there is a faster acceleration as we go further and further out. And dark energy refers to this force that is pushing us further and further out. Again, we use the word dark because we can't measure it directly along the way. So once again, here's our chart of the total of everything that is. Most of what is out there is not detectable. These, by the way, are numbers that are likely to shift as well. This one, not so much. It probably won't shift nearly as much as these two along the way. So just in the way that when I was studying this as a 101 and 102 level student 35 years ago, they didn't even mention dark matter. They didn't even mention dark energy. It was so mysterious back then that they didn't even want to confound any ideas in the 101 students. So again, this sort of shows the progress that we made just in my lifetime. And we've got different types of ideas that have come around. And you can sort of see the 1970s, we thought, okay, there's dark matter and there's ordinary matter. Then we had this idea of exotic dark matter because some of it seemed to be pushing rather than pulling. Well, when it's pushing rather than pulling, that's really dark energy rather than dark matter. And so our ideas of how the universe shift over time. So my advice to you, if you're going to become a cosmologist or an astrophysicist, is study the history of these things, but don't get too wedded to any one idea at any given time, because I guarantee it's going to change in this area here. So dark matter keeps changing, new and improved. I love the mystery flavor here. What's the net weight? We don't know. What are the ingredients? No one really knows, but if you figure it out, let us know, and we'll give you a Nobel Prize for it too. So the history of the universe in terms of the Big Bang expansion, here we are. And when we talk about accelerated expansion, right now we're not talking about like going from like that. It's going a little bit faster. As you can sort of see, it's edging up here, but it's not sort of rip-roaring apart, at least not yet. So we start from a very small space. We have a rapid expansion as the radiation pushes out, and perhaps dark energy is in there as well, pushing out. Chances are good. And then it begins to solidify into protons and electrons and other pieces that then begin to form what we understand. This is sort of the limit of where we can see this afterglow, which is partly the cosmic background radiation. So this early portion of the universe that goes from this to this and then up is called the inflation era. And we call that the inflationary model. Again, this is a change over the past generation, where we thought it sort of started and just went out, and now we know it went up and then out in different ways. But they both of these models converge at a certain point and continue on from there. As I mentioned before, our ant on the balloon analogy, the larger the balloon, the less of a curvature the ant's going to see. So you make that balloon larger and larger and larger, and it seems flat. We're living on a big sphere like that, which is why we can look around and everything looks flat. But you get in a plane, if you're on a flat map and you're on a plane to Iceland like I am, and if you take the flat way, that's actually going to add 1,000 miles or more than if you're flying around the curve. From Chicago to Keflavik, I usually get about 3,000 miles in terms of my frequent flyer miles. But if we're dealing with it going on what we would see a flat Mercator projection map, that would actually add up to more than 4,000 miles if we were to do just a straight ruler kind of thing. And that's one of the ways in which we have always known, at least in the aviation era, that the world is curved, because our planes actually fly on a curve around the world rather than in a straight line around the world. Of course, we've known about the curvature of the Earth for much longer than that. As we're looking out into space, the curvature of space becomes the new thing that we need to figure out. And it becomes one of those things where the Big Bang modeling is important, understanding dark energy and dark matter is important, understanding our cosmic background radiation is important to figure out what kind of curvature we have. As we look back into the very, very earliest of times, again, we have our electromagnetic force, which we're very familiar with. We have our gravity, which we're very familiar with. Strong and weak nuclear forces, we don't experience those so much in everyday life, but those are the things that are at play at the atomic level and subatomic levels. But as we model the things in our universe mathematically, we can see the just like we talked about James Clerk Maxwell, that was in a much earlier lecture. He figured out that the equations over here for electricity and the equations over here for magnetism really look similar, and they can actually be one set of equations. We've been able to figure out the strong and weak nuclear forces and how the mathematics work for them and how they work together with the electromagnetic force. We have not yet been successful with this branch, putting gravity into this. We know it's there, we know it works somehow, but we don't know exactly what it is. We call that, when we get to it, the grand unified theory, the gut theory. We do not have that yet along the way. But one of the interesting things that is a corollary idea is that the Big Bang started out as a cosmic singularity. You might recognize that name, singularity, because that's what's at the center of a black hole. So there is one idea that we're actually inside a black hole that has expanded or erupted in some way. When we're looking at the universe, we're looking at big structures, but at the smallest level, again, where we have those strong and weak forces, we're talking about quantum kinds of ideas. And those quantum ideas are what are throwing things off with regard to gravity. We have a couple of different gravity theories right now there. But when we're talking about the very, very earliest universe, and we're talking about way, way, way before even the first second, we're talking about something that can be as small or smaller than an atom. And so quantum forces are important to apply there. But as we have our rapid expansion, our inflationary period here, our universe goes from being the size of something much smaller than an atom to the size of a softball. Ooh, look how big. But that's important because the stuff begins to separate out and stuff begins to solidify. And after that, we enter the particle era, where we end up with things beginning to cool off because things aren't bumping into each other quite as much. And as that happens, we go from our phases, just like we have here on our planet. Things that are hot are gaseous. As they cool, they turn into liquid. As they cool more, they turn into solid. That's why we go from water vapor to rain to snow. So we do have our sequences that are happening there. And the formation of baryons, which is protons and neutrons and such, is called baryogenesis. And this happens when we have a large enough and cool enough area. We have protons and neutrons, we have electrons, we also have positrons, which are sort of anti-electrons. Did we have anti-protons and anti-neutrons in any major force? And what would an anti-neutron really be if they're neutral? That would be an interesting thing, and we haven't figured that out yet either. That's one of the areas we're still working on. So as things began to cool off and solidify, I hate to use the word solidify there technically, but you get the idea. things were forming into mostly hydrogen and helium. We still see that as the principal components of our universe today. And the principal universal components were there within the first 3 minutes, and we still have that around. And we're still expanding, things are still cooling. Electrons begin to form into specific atoms with the protons from the hydrogen, as well as the nuclei that were made for helium. And we call this sort of recombination, and what happens to our general electrons and photons that are out there still separated along the way. Well, that's in part where we get our cosmic background radiation. So we have all of these things that are happening along the way. Notice we have our combination, recombination, our sort of dark period here, because stars have not formed yet, but the radiation that's in there has dissipated far enough that it's not glowing anymore. So we did have a dark ages of our universe that lasted for 100 million years or more. And then we began to have formation of what we see today. So these are the things that we are looking at: cosmic expansion, nucleosynthesis, and our cosmic background radiation. What do we know in terms of our observational evidence of the Big Bang? And how do we figure out that this works with Hubble? So those are the things to understand with regard to that. But we do have some paradoxes. With expansion inflation explains why things are uniform. Things are sort of the same over there as they are here, because once upon a time we were closer together. Right now, if the universe is 17 or is 13.5 billion years old, that means we're talking 27 billion light years across from this point to this point. And in fact, it's even larger because we had those acceleration points along the way, but things over here look like things over here. And why do things over here look like things over here if they don't have enough time in the life of the universe to communicate with each other? And that again is because once upon a time they were much closer together and they were formed at that point. Here again we have our curvature areas. And when we're talking about sort of going back into the big crunch, we call that a positive curvature. We're sort of positive, we're going back into what we were. If we're expanding forever, we're in the saddle universe here. We call that a negative curvature. And of course, if we're just sort of halfway in between, just sort of trucking along, but staying pretty uniform, we call that a flat curvature. So critical density is the most important thing. The higher the density, the more likely we are to have a positive curvature. The lower the density, the more likely we are to have a negative curvature. And we call that the omega, sort of the omega. If we have an omega that's less than 1, we sort of keep going forever. If we have a curvature, an omega that's greater than 1, then we actually crunch back in. But as we're sort of looking, we are seeing the expansion going and going and going. So in our local area, it looks flatter and flatter and flatter as we expand more and more. So when we're looking at the earliest of early times, we reach a point where we think that relativity is no longer operative. That's not unusual in science. Newton's ideas work almost perfectly well for most of the planets, except for extreme cases like Mercury. But when we go to the moon and when we go to Mars, we're pretty much doing what Newton told us to do. But you get into areas where Newton doesn't apply anymore and we have to go to Einstein. Well, we're reaching to the point where Einstein doesn't even apply anymore, and we're looking for things at the Big Bang and what maybe came before the Big Bang as well. And that's one of the greatest mysteries in our time. So I invite you to think about all of that, and I thank you for being part of this. And we'll have our final chapter in the book next week.